stop what you're doing right now. Seriously. Because what I'm about to tell you is going to fundamentally change how you understand the scale of the universe. Right now, at this very moment, there is a star out there in the cosmos so incomprehensibly massive that if you placed it where our sun is, its surface would extend past the orbit of Saturn. Not Mercury, not Venus, not Earth, not Mars, not even Jupiter. Saturn, the sixth planet in our solar system, would be inside this star. Let me put that in perspective for you. Light, traveling at 299,792 kilometers per second, fast enough to circle Earth 7 times in 1 second, would take over 9 hours to travel from one side of this star to the other. It takes light just 4.6 seconds to travel from the sun to Earth. This star? 9 hours across. And here's what's absolutely mind-blowing. We just discovered it. Well, not just discovered it. We've known it existed for a while. But we've only recently confirmed that it's the largest star we've ever found in the entire observable universe. Its name is Stephenson 2-18. And it's not just big. It's not just huge. It's so monstrously, apocalyptically, universe-breakingly massive that it challenges our very understanding of how large a star can physically become before it tears itself apart. But here's where it gets interesting. This star shouldn't exist. According to our models of stellar physics, stars this large should be impossible. They should rip themselves to pieces under their own radiation pressure. They should explode. They should do anything except sit there calmly burning fuel like some kind of cosmic overachiever. Yet there it is, sitting 19,000 light years away from Earth, in a star cluster we didn't even know existed until relatively recently, burning with the power of 500,000 suns, completely ignoring everything we thought we knew about the limits of stellar evolution. Today, we're going to explore this monster. We're going to understand how it formed, why it exists, what it's doing right now, and what its eventual fate will be. We're going to compare it to other cosmic giants and understand where it fits in the hierarchy of stellar behemoths. We're going to talk about the star cluster it calls home and why that cluster is one of the most fascinating objects in our galaxy. And most importantly, we're going to explore what this star tells us about the universe itself, about the conditions that allow such monsters to form, about the limits of physics, and about the incredible diversity of cosmic phenomena that exist out there in the vast darkness of space. Because Stephenson 2-18 isn't just a big star. It's a window into the extreme physics of the universe, a laboratory for understanding stellar evolution at scales we can barely comprehend, and possibly a preview of the kinds of objects we'll discover as our telescopes get better and our understanding deepens. So buckle up. We're about to explore the biggest star in the known universe. And trust me, it's weirder and more wonderful than you can possibly imagine. Part 1, The Monster in the Darkness. Chapter 1, The Discovery of Something Impossible. The story of Stephenson. 2-18 begins not with its discovery, but with the discovery of its home, a massive star cluster called Stephenson 2. In 1990, astronomer Charles Bruce Stephenson was conducting a survey of red stars in the Milky Way. He was using photographic plates, yes, actual physical photographs of the sky, taken by the Palomar Observatory Sky Survey. He was looking for heavily reddened stars, which are stars whose light has been significantly affected by interstellar dust. And he found something weird. In the constellation Scutum, about 19,000 light-years away, there was a concentration of extremely red, extremely bright stars all clustered together. This wasn't just a random grouping. This was clearly a legitimate star cluster, and it was massive. But here's the thing, nobody had ever noticed it before. How do you miss an entire star cluster containing some of the largest stars in the galaxy? The answer is dust. Stephenson 2 is located right in the galactic plane, embedded in massive clouds of interstellar dust that absorb and scatter light. In visible wavelengths, you literally cannot see this cluster. It's hidden behind a curtain of cosmic debris. But in infrared wavelengths, which can penetrate dust much more effectively, the cluster becomes visible. And what Stephenson found was extraordinary. A cluster containing at least 26 red supergiants, which is an unusually high concentration of these rare, massive stars. Red supergiants are already bizarre objects. They're stars in the late stages of their lives, having exhausted the hydrogen in their cores and expanded to enormous sizes while burning heavier elements. Our sun will never become a red supergiant. It's not massive enough. Only stars born with at least 8 to 9 times the sun's mass eventually become red supergiants. But Stephenson 2 wasn't just home to any red supergiants. It contained some of the largest red supergiants ever discovered. And the largest of them all? That would be Stephenson 218. Chapter 2: Measuring the Unmeasurable. Here's the problem with measuring stars that are 19,000 light-years away. It's really, really hard. When we look at stars, even through our most powerful telescopes, they appear as points of light. We can't resolve their surfaces, can't see their features, can't directly measure their diameters the way you might measure a basketball. Instead, we have to use indirect methods, and each method comes with uncertainties and assumptions that can throw off our measurements. For Stephenson 2-18, astronomers used several techniques. Spectroscopy. By analyzing the star's light spectrum, we can determine its temperature. Stephenson 2-18 is cool for a star, about 3,200 Kelvin at its surface compared to the Sun's 5,800 Kelvin. This low temperature is actually crucial for the star being so large, and we'll get to why in a moment. Luminosity measurements. By measuring how bright the star appears from Earth and knowing its distance, we can calculate its actual luminosity, how much energy it's really putting out. Stephenson 218 is incredibly luminous, roughly 440,000 times brighter than the Sun. Some estimates put it even higher, at 630,000 solar luminosities. Stefan-Boltzmann law. This is where the magic happens. If you know a star's temperature and its luminosity, you can calculate its radius using the Stefan-Boltzmann law, which describes how much energy a black body radiates based on its temperature and surface area. When astronomers did this calculation for Stephenson 218, they got a number that seemed impossible. Approximately 2,150 times the radius of the Sun. Let me translate that into something more comprehensible. The Sun's radius is about 696,000 kilometers. Multiply that by 2,150,000 and you get approximately 1.5 billion kilometers. The distance from the Sun to Saturn averages about 1.4 billion kilometers. This star is larger than the orbit of Saturn. Chapter 3. The Uncertainty Problem. Now, before we go any further, we need to address something important. These measurements come with significant uncertainty. The exact size of Stephenson 218 is hotly debated in the astronomical community. Different studies, using different methods and different assumptions, have produced different results, ranging from about 1,500 solar radii on the conservative end to over 2,500 solar radii on the extreme end. Why is there so much uncertainty? First, measuring the star's distance is tricky. We know it's about 19,000 light-years away, but that "about" covers a range of several thousand light-years. If the star is closer than we think, it's less luminous than we calculated, which means it's smaller. If it's farther, it's more luminous and larger. Second, the star is variable. Red supergiants are notoriously unstable, constantly pulsating and changing in brightness and size. Stephenson 2-18 likely varies in radius by hundreds of millions of kilometers over time. So the question, how big is it, doesn't have a single answer. It depends on when you measure. Third, the star is surrounded by circumstellar material, dust and gas that it's blown off its surface. This material absorbs and re-radiates the star's light, making it difficult to determine where the star's surface actually ends and the surrounding material begins. And fourth, the theoretical models we use to interpret the data involve assumptions about the star's composition, mass loss rate, and evolutionary state. Change those assumptions, and you get different size estimates. So when I say Stephenson 2-18 is about 2,150 solar radii, understand that this is our best current estimate, but it could be somewhat smaller or somewhat larger. What we can say with confidence is this: Stephenson 218 is one of the largest stars we've ever discovered, and quite possibly the largest. Whether it's the largest or merely one of the top few depends on measurements that are still being refined. Chapter 4: A Tour of the Giant. Let's take an imaginary journey to Stephenson 218, because the only way to truly understand this object is to explore it at different scales. Imagine you're approaching the star from a great distance. At first, it looks like a dim red point of light. It's so cool that most of its energy is emitted in infrared wavelengths that your eyes can't see. But as you get closer, that point of light begins to resolve into a disk, and it keeps growing, and growing, and growing. By the time you're at a distance equivalent to the orbit of Neptune in our solar system, the star fills a significant portion of your view. It's a deep red, almost crimson sphere, with a surface that doesn't appear solid or well-defined, but rather fuzzy and indistinct, surrounded by shells of expelled gas and dust. If you continue inward to the orbit of Uranus, the star dominates half the sky. Its surface is churning with massive convection cells, bubbles of hot plasma rising from the interior, cooling and sinking back down. Each convection cell is larger than our entire sun. At the orbit of Saturn, you'd be skimming the star's outer atmosphere. The surface isn't a sharp boundary, but a gradual transition from the thin outer layers into denser regions below. The temperature here is about 3,200 Kelvin, hot enough to vaporize any spacecraft, but cool by stellar standards. Continue inward, past where Jupiter would be, past Mars, past Earth, and you're diving deeper into the star's envelope. The temperature and pressure increase gradually. The material around you is extraordinarily thin, much thinner than Earth's atmosphere at sea level. But it's incredibly hot. At the orbit of Mercury, you're deep inside the star, but you're still in the outer layers. The density here is still less than Earth's atmosphere, though the temperature has climbed to tens of thousands of degrees. Only when you approach the core, buried under hundreds of millions of kilometers of stellar material, do you encounter the truly extreme conditions. Here, temperatures reach hundreds of millions of degrees, and the pressure is billions of times Earth's atmospheric pressure. And here, in this cosmic furnace, nuclear fusion is taking place. But it's not the simple hydrogen fusion that powers normal stars like our Sun. No, Stephenson 218 is past that stage. It's now fusing helium into carbon and oxygen, and possibly fusing even heavier elements in its core. Chapter 5, the physics of being enormous. So how does a star get this big? And more importantly, why doesn't it just fall apart or explode? The answer lies in understanding stellar evolution and the delicate balance of forces that govern a star's structure. Normal stars, like our Sun, are in hydrostatic equilibrium. The inward pull of gravity is perfectly balanced by the outward pressure from nuclear fusion in the core. This balance keeps the star stable, but stars aren't static objects. As they age, they evolve, and their structure changes. Here's what happened to create Stephenson 218. Stage 1, the beginning. Stephenson 218 was born as a massive star, probably 15 to 25 times the mass of the Sun. It formed from the collapse of a giant molecular cloud, just like all stars do. For most of its early life, perhaps 10 to 20 million years, it was a blue supergiant, or a main sequence O-type star, incredibly hot and luminous, fusing hydrogen into helium in its core. Stage 2, core hydrogen exhaustion. Eventually, the hydrogen in the core ran out. For a massive star, this is just the beginning. The core contracts and heats up, while a shell of hydrogen around the core begins fusing. The extra energy from shell burning causes the outer layers of the star to expand dramatically. The surface moves farther from the core, cools down, and the star transitions from blue to red. Stage 3, red supergiant phase. Now the star is a red supergiant. Its core is fusing helium into carbon and oxygen, while shells around the core fuse hydrogen and helium. The star continues to expand. The outer layers are so far from the core that gravity barely holds them. The surface is cool, the atmosphere is extended, and the star becomes enormous. Stage 4, maximum expansion. At some point in its red supergiant phase, the star reaches its maximum size. This is where Stephenson 2-18 is now. Why doesn't it keep expanding forever? Several factors limit stellar size. The Eddington limit. This is the point at which a star's radiation pressure, photons pushing outward, equals the gravitational force pulling inward. Above this limit, radiation pressure would literally blow the star apart. For very luminous stars, the Eddington limit places an upper bound on how large they can be. Stephenson 2-18 is probably close to this limit. Mass loss. Red supergiants lose mass at prodigious rates. Stephenson 218 is probably shedding material equivalent to one Earth's mass every few thousand years. This mass loss removes the outer layers that would otherwise make the star even larger. Structural instability. At extreme sizes, stars become unstable. Pulsations, convection, and turbulence create a chaotic outer envelope. The star is constantly adjusting its structure in response to these instabilities. So Stephenson 218 is balanced on a knife's edge. It's as large as physics allows a star to be while remaining barely stable. Part 2. The Cosmic Context. Chapter 6. The Hierarchy of Giants. Stephenson 2-18 is massive, but it's not alone. Let's put it in context by comparing it to other giant stars. UY Scuti. For years, UY Scuti held the record as the largest known star, with estimates ranging from 1,700 to 1,900 solar radii. It's located about 9,500 light-years away in the constellation Scutum. Recent measurements suggest it might be smaller than previously thought, possibly around 1,500 solar radii, which would place it below Stephenson 2-18. VY Canis Majoris. This was the previous record holder before UY Scuti. Early measurements suggested it might be over 2,000 solar radii, but improved observations have revised this down to about 1,400 to 1,500 solar radii. It's extraordinarily luminous and surrounded by a massive nebula of ejected material. Betelgeuse. Probably the most famous red supergiant, Betelgeuse is the red star in Orion's shoulder. It's only about 700 to 900 solar radii, making it far smaller than Stephenson 218, but it's close enough, about 650 light-years, that we can study it in detail. WOHG 64. Located in the Large Magellanic Cloud, this red supergiant has an estimated radius of about 1,500 solar radii and is surrounded by a massive, dusty torus. RW Cephei. Another contender, with estimates ranging from 1,200 to 1,600 solar radii, depending on the measurement technique. The pattern you'll notice is that all these measurements are uncertain and contested. Measuring stellar radii at these extreme scales is difficult, and different teams using different methods get different results. What we can say definitively is that there's a group of red supergiants, including Stephenson 2-18, UY Scuti, VY Canis Majoris, and a few others, that represent the largest stars we know of. They're all roughly in the same size range, between about 1,500 and 2,500 solar radii. Stephenson 2-18 appears to be at the upper end of this range, making it the largest or one of the largest stars we've discovered. Chapter 7. Why red supergiants are so large. You might have noticed that all the largest stars are red supergiants. This isn't a coincidence. There are fundamental physical reasons why red supergiants achieve such enormous sizes. First, temperature matters. The size of a star is determined by its luminosity and temperature through the Stefan-Boltzmann law. For a given luminosity, a cooler star must have a larger surface area to radiate that energy. Red supergiants are cool, typically between 3,000 and 4,000 Kelvin, so even though they're very luminous, they need enormous surface areas to radiate all that energy at such low temperatures. Second, evolutionary stage matters. Red supergiants are evolved stars in late stages of stellar evolution. They've exhausted the hydrogen in their cores and are now burning heavier elements in shells around the core. This shell burning is highly efficient and produces enormous amounts of energy, which causes the outer layers to expand dramatically. The star is essentially inflating like a balloon. Third, these stars have lost significant mass. During their lifetimes, red supergiants eject enormous amounts of material through stellar winds. This mass loss reduces the surface gravity, allowing the outer layers to expand even further. Finally, the internal structure of red supergiants is unique. They have small, dense cores surrounded by enormous, tenuous envelopes. The outer layers are barely held by gravity and are extremely distended. All these factors combine to make red supergiants the largest type of star possible. But there's a catch. They don't stay this way for long. Chapter 8: The Stephenson 2-Star Cluster. To understand Stephenson 218, we need to understand its home, the Stephenson 2-Star Cluster. This cluster is extraordinary for several reasons. First, it's young. The stars in Stephenson 2 are only about 14 to 20 million years old. That might sound ancient, but in cosmic terms, it's practically newborn. For comparison, our Sun is 4.6 billion years old. Second, it's massive. The cluster contains at least 26 red supergiants, which is an unusually high concentration. Most star clusters don't have anywhere near this many red supergiants. Third, it's obscured. The cluster is located right in the galactic plane, embedded in dense molecular clouds that make it extremely difficult to observe invisible light. We can only really study it in infrared wavelengths. Fourth, it's a glimpse into stellar evolution at extreme masses. Because the cluster is young and all its stars formed at roughly the same time from the same material, we can study stars at different stages of evolution, but with similar ages. The red supergiants in Stephenson 2, including Stephenson 218, are stars that were born massive and are now in late evolutionary stages. They've already exhausted the hydrogen in their cores and are burning helium and heavier elements. Meanwhile, there are other stars in the cluster that are still on the main sequence, younger in their evolution despite being the same chronological age. These are less massive stars that evolve more slowly. By studying the cluster as a whole, astronomers can piece together a complete picture of how massive stars evolve and what determines their ultimate fate. Chapter 9: The Life Expectancy of a Giant. Stephenson 2-18 is living on borrowed time. Stars like our Sun can live for about 10 billion years, slowly and steadily fusing hydrogen into helium in their cores. But massive stars live fast and die young. A star like Stephenson 218, born with perhaps 20 to 25 solar masses, will live for only about 10 to 20 million years total. Given that the Stephenson 2 cluster is about 14 to 20 million years old, and Stephenson 218 is already in its red supergiant phase, this star is approaching the end of its life. How much time does it have left? That's difficult to say precisely, but probably between 100,000 and a few million years. In cosmic terms, it could explode tomorrow or in a million years. Both are equally soon. Here's what we know about its current state. The core is currently fusing helium into carbon and oxygen. This process is much faster than hydrogen fusion. It might take only a million years or so. Once the helium is exhausted, the core will contract and heat up further, and a new fusion process will begin. Carbon burning, then neon, then oxygen, then silicon. Each successive stage happens faster than the last. Carbon burning might take 10,000 years. Neon burning might take a few years. Oxygen burning might take a few months. Silicon burning, the final stage, takes about 1 day. Then the core can't fuse anything else. Silicon fuses into iron, but iron fusion consumes energy rather than releasing it. Once an iron core forms, the star's fate is sealed. Chapter 10: The Final Countdown. Let me walk you through the final hours of a star like Stephenson 2-18, because it's one of the most dramatic events in the universe. The iron core grows as silicon fusion continues in a shell around it. Iron accumulates in the core, but it can't fuse. Doing so would consume energy, and the core needs to release energy to support itself against gravity. The core keeps growing. When it reaches about 1.4 solar masses, the Chandrasekhar limit, something catastrophic happens. The core can no longer support its own weight. In a fraction of a second, it collapses. The collapse is extraordinarily rapid. The core, about the size of Earth, collapses to a sphere about 20 kilometers across in less than a second. Protons and electrons are crushed together to form neutrons, releasing a vast flood of neutrinos. The outer layers of the star, suddenly deprived of support, begin to fall inward. They're falling toward the core at speeds approaching 70,000 kilometers per second, about 23% the speed of light. When this infalling material hits the incompressibly dense neutron core, it rebounds. A shock wave forms and propagates outward through the star. For several hours, this shock wave stalls as it loses energy, disintegrating iron nuclei and heating material. But then the delayed neutrinos from the core. There are so many that even though they barely interact with matter, they carry enough energy. Revive the shock wave. The shock breaks through the surface of the star. Everything outside the neutron core, millions of Earth masses of stellar material, is blasted into space at thousands of kilometers per second. The star has just gone supernova. For a few weeks, this supernova will shine with the brightness of an entire galaxy. It will be visible from Earth in broad daylight, assuming we're still around when it happens. The explosion will enrich the surrounding interstellar medium with heavy elements forged in the star's core and in the explosion itself. These elements, carbon, oxygen, iron, gold, platinum, and many others, will eventually be incorporated into new stars, planets, and maybe even new forms of life. And at the center, where once there was a stellar core, there will now be a neutron star, a sphere of neutrons about 20 kilometers across, spinning rapidly, perhaps hundreds of times per second, with a magnetic field trillions of times stronger than Earth's. Or, if the core is massive enough, even a neutron star can't support it. In that case, the core continues to collapse, shrinking beyond the neutron star state, past any possible source of resistance, until it crosses the event horizon and becomes a black hole. For Stephenson 2-18, which was probably born with 20 to 25 solar masses and has since lost significant mass through stellar winds, the outcome is uncertain. It might leave behind a neutron star, or it might form a black hole. We won't know until it actually explodes. But one thing is certain: when Stephenson 2-18 dies, it will be spectacular. Part 3: The Science of Extremes. Chapter 11: The Theoretical Limits of Stellar Size. Now that we understand what Stephenson 2-18 is and how it got so large, let's dive into a fascinating question. Is there a maximum size for a star? Can you know? Stars get even bigger than Stephenson 2-18, or have we found the upper limit? The answer is complicated, and it involves some beautiful physics. There are several factors that limit how large a star can become. The Eddington luminosity limit. This is perhaps the most fundamental constraint. Arthur Eddington discovered that for any given stellar mass, there's a maximum luminosity the star can have before radiation pressure overcomes gravity. Here's how it works. Photons carry momentum. When a photon is absorbed by an atom, it transfers that momentum, creating an outward force. In a very luminous star, the outward force from radiation can become strong enough to counteract gravity. The Eddington limit depends on the star's mass and composition. For a star like Stephenson 2-18, the Eddington luminosity is probably around 500,000 to 1 million times the Sun's luminosity. Stephenson 2-18, with a luminosity of roughly 440,000 to 630,000 solar luminosities, is operating very close to this limit. If it became much more luminous, radiation pressure would literally blow the outer layers into space. Mass loss through stellar winds. Red supergiants experience tremendous mass loss through stellar winds. This isn't the gentle solar wind our sun produces. This is a hurricane of stellar material streaming away from the star at speeds of tens of kilometers per second. Stephenson 2-18 is probably losing mass at a rate of about 1 Earth mass every few thousand years. That might not sound like much, but over hundreds of thousands of years, it adds up. This mass loss serves two purposes. It removes the outer layers that make the star large, and it reduces the star's total mass, which affects all its other properties. There's a feedback loop at work. As the star gets larger and more luminous, mass loss increases. Increased mass loss removes material and eventually limits how large the star can grow. Dynamical instability. At extreme sizes, stars become dynamically unstable. The outer layers are so loosely bound that pulsations, convection, and turbulence can cause major structural changes. Some red supergiants vary in brightness by more than a magnitude, a factor of 2.5, over periods of months to years. This variability is driven by fundamental pulsations, the entire star expanding and contracting. When a star gets too large, these pulsations can become so violent that they eject material or even disrupt the star's structure entirely. Opacity and energy transport energy must flow from the core, where it's generated, to the surface, where it's radiated away. In very large stars, this energy transport becomes increasingly difficult. The opacity, how easily material absorbs photons, increases with certain elements. If the star becomes too large and the outer layers too dense, energy can't escape efficiently, and the star's structure becomes unstable. Putting it all together, when you combine all these constraints, you get a maximum possible stellar radius of somewhere around 2,500 to 3,000 solar radii for the most massive red supergiants. Stephenson 2-18, at approximately 2,150 solar radii, is approaching this theoretical maximum. Stars significantly larger than this are probably impossible under normal stellar physics. However, and this is important, there might be exotic scenarios we haven't considered. Extremely unusual chemical compositions, rapid rotation, or other factors might allow slightly larger stars to exist. But based on our current understanding, Stephenson 2-18 is about as large as stars can get. We might discover slightly larger stars in the future, but we're unlikely to find anything dramatically bigger. Chapter 12. What we can learn from observing giants. Stephenson 2:18 and stars like it are more than just cosmic curiosities. They're natural laboratories for studying physics under extreme conditions we can't replicate on Earth. Stellar evolution. Models. By observing stars at different evolutionary stages, we can test and refine our models of how stars live and die. Stephenson 2 cluster gives us a snapshot of massive star evolution. We see stars on the main sequence, stars transitioning to red supergiants, and stars in late red supergiant phases, all at roughly the same age. By comparing observations to theoretical predictions, astronomers can verify their models or discover where the models need improvement. For instance, the sheer number of red supergiants in Stephenson 2 is higher than some models predicted. This suggests that our understanding of how long stars spend in the red supergiant phase might need adjustment. Mass loss mechanisms. How exactly do red supergiants lose mass? The mechanisms aren't fully understood. Is it primarily through steady stellar winds? Through episodic mass ejections? Through pulsation-driven shocks? Some combination? By studying stars like Stephenson 2:18, observing their variability, their surrounding nebulae, the velocity of ejected material, we can piece together the mass loss story. This matters because mass loss determines the star's ultimate fate. How much mass a star retains affects whether it leaves behind a neutron star or a black hole when it explodes. Nucleosynthesis. Red supergiants are cosmic forges, creating heavy elements through nuclear fusion. By analyzing the spectrum of stars like Stephenson 2-18, we can determine which elements are present in their atmospheres. This tells us about the fusion processes happening in the core and about the mixing processes that bring core material to the surface. When these stars eventually explode, they'll seed the galaxy with these heavy elements. Understanding stellar nucleosynthesis is crucial for understanding galactic chemical evolution, how the composition of the galaxy changes over time. Circumstellar envelopes. Stephenson 2-18 is surrounded by material it has ejected. Circumstellar envelope of dust and gas. This envelope isn't uniform. It has structure, with shells, clumps, and asymmetries that reveal the history of the star's mass loss. By studying these envelopes with infrared telescopes and radio observations, we can map the distribution of material and learn about the ejection process. Some red supergiants have spectacular nebulae around them. VY Canis Majoris, for instance, is surrounded by a complex nebula showing evidence of multiple ejection episodes. Stephenson 2:18's circumstellar envelope is less well studied, partly because the star is more distant and heavily obscured by interstellar dust. But ongoing observations are revealing its structure. Supernova progenitors. One of the biggest questions in astrophysics is, which stars produce which kinds of supernova? Not all supernova are the same. Type 2 supernovae come from massive stars, but they show a diversity of properties. Some are very bright, some are dim, some eject lots of material, some eject less. Some leave behind neutron stars, some leave black holes. By studying stars like Stephenson 2:18 before they explode, we can better predict what kind of supernova they'll produce. Stephenson 2 cluster is particularly valuable because it contains many massive stars at different evolutionary stages. When these stars eventually explode, and many will over the next few million years, we'll be able to correlate the pre-supernova properties with the explosion characteristics. Chapter 13, the observational challenges. Studying Stephenson 2 to 18 is extraordinarily difficult. Let me explain why. Distance. At 19,000 light-years, the star is far enough that even with our best telescopes, it appears as a point of light. We can't resolve the surface, can't see features, can't directly image the star's shape. This means we rely entirely on indirect methods to determine its properties. Spectroscopy, photometry, modeling, interstellar extinction. Between us and Stephenson, 2 to 18 are 19,000 light-years of interstellar space, filled with dust and gas. This material doesn't just make the star dimmer, it also changes the color of the light. Blue light is scattered and absorbed more than red light, so the star appears redder than it actually is. Astronomers have to correct for this interstellar reddening, but the corrections depend on assumptions about the amount and properties of intervening dust. Get those assumptions wrong, and your measurements are off. Intrinsic variability. Stephenson 2-18 varies in brightness over time. This makes it difficult to get consistent measurements. Is the star dim because it's in a pulsation minimum, or because there's more dust between us and it? Did the luminosity really change, or did the circumstellar envelope change how much light it absorbs and re-radiates? To get accurate measurements, you need long-term monitoring to average out the variability. Circumstellar dust. The star is surrounded by dust that it has ejected. This dust absorbs the star's light and re-radiates it at longer wavelengths. When we measure the star's brightness, we're seeing a combination of direct starlight and re-radiated light from the dust. Separating these components requires careful modeling. If we don't account for the dust correctly, we'll overestimate or underestimate the star's true luminosity and size. Model dependence. All our measurements depend on models. We use models of stellar atmospheres to interpret spectra. We use models of stellar structure to understand the star's internal properties. We use models of interstellar extinction to correct for dust. Different models give different results. The uncertainty in Stephenson 2-18 size comes largely from these model dependencies. As our models improve and our observations get better, our measurements will become more accurate. But for now, we're dealing with significant uncertainties. Future observations. Several upcoming telescopes and instruments will help us study Stephenson 2-18 better. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, can peer through the dust and study the star and its circumstellar envelope in unprecedented detail. The Extremely Large Telescope, ELT, currently under construction in Chile, will have unprecedented resolution and light-gathering power, allowing more detailed spectroscopic studies. Long baseline infrared interferometry could potentially resolve the star's surface, allowing direct size measurements rather than relying entirely on indirect methods. In the coming decades, our understanding of Stephenson 2-18 will improve dramatically as these new capabilities come online. Chapter 14, the comparison game. Let's do some fun comparisons to really drive home how absurdly large Stephenson 2-18 is. Stephenson 2-18 versus the Sun. If you placed Stephenson 2-18 where the Sun is, its surface would extend beyond Saturn's orbit, Mercury, Venus, Earth, Mars, and Jupiter would all be inside the star. Saturn, at its average distance of 1.4 billion kilometers, would be near or just beyond the star's surface. Light would take 9+ hours to travel from one side of the star to the other, compared to 4.6 seconds from the Sun to Earth. The volume of Stephenson 2-18 is approximately 10 billion times the volume of the Sun. If the Sun were a ping pong ball, Stephenson 2-18 would be a sphere 45 meters, 150 feet, in diameter. Stephenson 2-18 versus Earth. You could fit about 2.5 billion Earths across the diameter of Stephenson 2-18. The star's volume is roughly 13 quintillion, 13 times 10 to the power of 18, times Earth's volume. If you could drive a car at highway speed, 100 kilometers per hour, around Stephenson 2-18's equator, it would take about 3,600 years to complete one lap. A commercial jet flying at 900 kilometers per hour would take 400 years to circle the star Stephenson 2-18 versus other cosmic objects. Stephenson 2-18 is about 3 times larger than Betelgeuse. It's roughly 1.5 times larger than UY Canis Majoris, based on current estimates. It's comparable in size to UY Scuti, possibly slightly larger. However, it's far smaller than some planetary nebulae and supernova remnants, which can be light years across. It's absolutely tiny compared to galaxies. The Milky Way is about 100,000 light years across, while Stephenson 2-18 is about 0.2 light hours across Stephenson 2-18 versus density. Here's where it gets really weird. Despite its enormous size, Stephenson 2-18's average density is incredibly low. The average density of the star is roughly 0.000005 times the density of Earth's atmosphere at sea level. In the outer regions of the star, the density is even lower, comparable to what we'd call a vacuum in a laboratory. You could literally wave your hand through the outer layers of the star without encountering much resistance. You'd just be instantly vaporized by the heat, so don't try this. Despite this incredibly low density, the star contains 15 to 20 times more mass than the Sun, all because of its absolutely enormous volume. Chapter 15: The Energy Output. Let's talk about how much energy Stephenson 2-18 is producing, because the numbers are staggering. The star's luminosity is approximately 440,000 to 630,000 times that of the Sun. Let's use 500,000 as a middle estimate. The Sun outputs about 3.828 times 10 to the power of 26 watts. That's 382.8 septillion watts, or about 382.8 trillion watts. Multiply that by 500,000, and Stephenson 2-18 is outputting about 1.9 times 10 to the power of 32 watts. To put that in perspective, energy per second. Stephenson 2-18 outputs more energy every second than the Sun outputs in 5.8 days. Energy per day. Every day, the star outputs more energy than the Sun will produce in about 1,370 years. Energy per year. The annual energy output equals what the Sun will produce over about 500,000 years. Total energy budget? If the star lives another 1 million years as a red supergiant, it will output as much energy as the Sun will produce over 500 billion years, far longer than the Sun will actually exist. Comparison to human energy use. Humanity currently uses about 580 million terajoules of energy per year, or about 1.8 times 10 to the power of 13 watts average power. Stephenson 2 to 18 outputs about 10 to the power of 19 times more power than all of human civilization. In other words, the star produces in 1 second what humanity uses in 16 million years. Comparison to supernova. When Stephenson 2-18 eventually explodes as a supernova, it will briefly outshine its current luminosity by a factor of about 10,000 to 100,000. For a few weeks, this single exploding star will be outputting energy at a rate comparable to an entire small galaxy. Where does all this energy go? Most of it is radiated as light, primarily in the infrared portion of the spectrum, since the star is so cool. Some energy goes into the stellar wind, accelerating material away from the star. Some goes into heating the circumstellar dust, which then re-radiates it at even longer wavelengths. And a tiny fraction, a vanishingly small percentage, will eventually reach Earth 19,000 years after it left the star, contributing a few photons to our telescopic observations. Part 4. The broader implications. Chapter 16. What this tells us about the universe. The existence of Stephenson 2-18 isn't just a neat astronomical fact. It tells us profound things about the universe we live in. Star formation at extreme masses. First, it tells us that nature can and does form extremely massive stars. The processes that lead to star formation, the collapse of molecular clouds under gravity, the fragmentation of those clouds into individual protostars, the competition for material between forming stars, can sometimes produce monsters. In the Stephenson 2 cluster, conditions 15 to 20 million years ago were right for forming many massive stars. What were those conditions? Probably a very massive, dense molecular cloud with relatively little turbulence. In turbulent clouds, fragmentation produces many small stars. In calmer, denser clouds, you can get fewer, more massive stars. The metallicity, abundance of elements heavier than hydrogen and helium, also matters. The material that formed Stephenson 2 probably had similar composition to the Sun. Not pristine primordial gas, but enriched by previous generations of stars. The upper mass limit. There's a long-standing question in astrophysics. What's the maximum mass for a star? Theory suggests there should be an upper limit around 150 to 300 solar masses, depending on metallicity. Above this, the star becomes unstable during formation or shortly after. Stephenson 2-18 probably formed with 20 to 25 solar masses, well below this theoretical limit. But it's part of a cluster containing many massive stars, and studying them collectively helps us understand the upper end of the stellar mass distribution. Chemical enrichment stars like Stephenson 2-18 are crucial for the chemical evolution of galaxies. When the star formed, it incorporated material from previous stellar generations. During its life, it's fusing hydrogen into helium, helium into carbon and oxygen, and creating heavier elements. When it explodes, it will return this enriched material to the interstellar medium, increasing the metallicity of the gas that will form future stars. Over cosmic time, Successive generations of stars gradually increase the heavy element content of the galaxy. We live in a metal-rich epoch compared to the early universe. Stephenson 2-18 and stars like it are essential drivers of this enrichment process. Dust production. Red supergiants are major sources of cosmic dust. The circumstellar envelope around Stephenson 2-18 contains dust grains that condensed from material the star ejected. These grains are made of carbon, silicates, and other materials, forged in the stellar interior. When the star eventually explodes, this dust will be scattered across a huge region of space, along with new dust formed in the supernova ejecta. This dust is important for several reasons. It's the raw material for forming planets in future stellar systems. It affects the temperature and chemistry of the interstellar medium. It influences how light travels through galaxies. It provides surfaces where complex molecules can form the supernova rate. By understanding how many massive stars exist and how they evolve, we can estimate the supernova rate in our galaxy. The Milky Way experiences roughly 1 to 2 supernovae per century on average. Most of these are not visible from Earth because they're obscured by dust or occur on the far side of the galaxy. Stephenson 2 cluster, with its many massive stars, will contribute several supernovae over the next few million years. Clusters like this are supernova factories. These explosions will shape the surrounding interstellar medium, triggering new star formation, creating cavities and bubbles in the gas, and dispersing heavy elements. Chapter 17. The Fate of Stephenson 2-18. We've mentioned that Stephenson 2-18 will eventually explode as a supernova, but let's explore its final fate in more detail. Pre-supernova evolution. In the coming hundreds of thousands to few million years, Stephenson 2-18 will continue fusing heavier elements in its core. It might undergo additional changes. It could experience a blue loop, where it temporarily becomes hotter and smaller before expanding again. It might undergo increased mass loss, shedding its outer layers more rapidly. It could develop more extensive circumstellar structures as mass loss accelerates. It might experience increased variability as internal instabilities grow. Some models predict that the most massive red supergiants undergo a phase called a luminous blue variable, LBV, before finally exploding. In this phase, the star becomes unstable and experiences dramatic eruptions. Whether Stephenson 2-18 will become an LBV is uncertain. It depends on its exact mass, rotation, and other factors we don't know precisely. The supernova itself. When the star finally exhausts its nuclear fuel and the core collapses, the resulting supernova will be spectacular. It will probably be a Type 2 supernova, specifically a Type 2P, plateau, or possibly a Type 2B, if the star has lost much of its hydrogen envelope. The explosion will reach peak brightness of about 10 billion times the sun's luminosity, be visible across the galaxy and even in nearby galaxies, eject 10 to 20 solar masses of material at speeds of 10,000 to 30,000 kilometers per second, create a rapidly expanding shockwave that will sweep up surrounding material, forge elements heavier than iron through rapid neutron capture, the R process, shine primarily in visible light for weeks to months, then fade gradually over years, from Earth if we're still around, and if the supernova is oriented toward us, and not too obscured by dust, it could be a spectacular sight. At 19,000 light-years distance, the supernova would reach an apparent magnitude of roughly -8 to -10, making it about as bright as the quarter moon. It would be easily visible in daylight and would cast shadows at night. However, given the heavy obscuration towards Stephenson 2, it might be significantly dimmed in visible light. We'd see it best in infrared wavelengths. The remnant. After the explosion, what remains? The core will collapse to form either a neutron star or a black hole. For a star that formed with 20 to 25 solar masses, the final outcome depends critically on how much mass was lost during the red supergiant phase. If the star has lost enough mass that the final core is below about 25 to 30 solar masses at the moment of collapse, it will form a neutron star, a sphere about 20 kilometers across, composed almost entirely of neutrons, with a mass of 1.4 to 2.5 solar masses. This neutron star will probably be spinning rapidly, hundreds of rotations per second, and have an extremely strong magnetic field. It might be observable as a pulsar, emitting beams of radiation that sweep across space like a cosmic lighthouse. If the core is more massive, above about 25 to 30 solar masses, not even neutron degeneracy pressure can support it. The core will continue collapsing past the neutron star state, past any possible form of resistance, until it forms a black hole. The black hole will have a mass of perhaps 10 to 20 solar masses, depending on what fraction of the core material escapes in the explosion. Its event horizon will be about 30 to 60 kilometers in radius. This black hole will be invisible directly, but it might be detectable through X-ray emission if it's accreting material, gravitational effects on nearby stars or gas, gravitational waves if it eventually merges with another black hole. The supernova remnant, the ejected material, will continue expanding for tens of thousands of years, creating a supernova remnant. This remnant will be a complex, beautiful structure, a central region containing the neutron star or black hole, a shell of ejected stellar material enriched with heavy elements, swept up interstellar gas, shocked and heated to millions of degrees, magnetic fields tangled and amplified by the explosion, cosmic rays accelerated to near light speeds. The remnant will be visible in X-rays, radio waves, and optical light for tens of thousands of years before gradually fading and dispersing into the interstellar medium. Chapter 18, Stephenson 2:18 in cultural context. While Stephenson 2:18 isn't as famous as Betelgeuse or as well known as UY Scuti, it has captured the imagination of astronomy enthusiasts around the world. The scale obsession. Humans have always been fascinated by superlatives. The biggest, the tallest, the fastest, the oldest. In astronomy, this manifests as an obsession with finding the biggest star, the largest galaxy, the most massive black hole. Stephenson 2:18 appeals to this instinct. It's not just big, it's possibly the biggest. And that matters to people, even though the difference between 2,000 and 2,150 solar radii is academically interesting, but experientially meaningless. The humility factor. Learning about objects like Stephenson 2:18 provides perspective. Earth, which seems so large and important to us, could fit across the diameter of this star 100 to 10,000 times. The entire orbit of Saturn, which takes 29 years to complete, would fit inside the star. This is simultaneously humbling and awe-inspiring. We're tiny, but we're also the only things that we know of capable of comprehending our tininess and appreciating the vast scale of the cosmos. The temporary nature of knowledge. The history of largest known star is a reminder that scientific knowledge is always provisional. For years, VY Canis Majoris was considered the largest. Then better measurements revised its size downward. Then UY Scuti took the record. Then better measurements made that uncertain. Now Stephenson 2-18 appears to be the largest, but future observations might revise its size, or discover an even larger star, or confirm that one of the other candidates is actually bigger. This isn't a failure of science. It's how science works. We make our best measurements with current technology, acknowledge uncertainties, and update our understanding as new data arrives. The communication challenge. Explaining Stephenson 2-18 to the public is challenging because the scales involved are literally incomprehensible. You can say 2,150 times the sun's radius, but most people don't have an intuitive sense of the sun's radius to begin with. You can say larger than Saturn's orbit, and that's better, but still abstract unless you really understand orbital mechanics and planetary distances. The best analogies involve scaling down to familiar sizes, but even then, the brain struggles with the numbers. This is why visualization matters. Videos, animations, and scale comparisons help make the abstract concrete. Seeing a simulation where planets are engulfed by an expanding red supergiant creates an emotional impact that raw numbers don't. Chapter 19: The Unanswered Questions. Despite everything we've learned about Stephenson 2-18, major questions remain. Exact size. We still don't know the star's exact size within a few hundred solar radii. Better observations, particularly high-resolution infrared interferometry, could nail this down more precisely. Mass and mass loss rate. We have rough estimates of the star's current mass, probably 15 to 20 solar masses, and its mass loss rate, probably losing material equivalent to one Earth mass every few thousand years. But these need refinement. More detailed spectroscopic studies could better constrain both values. Internal structure. What exactly is happening inside the star? Is there active convection throughout the envelope? How much mixing occurs between the core and outer layers? What's the composition profile as a function of depth? Advanced stellar modeling combined with asteroseismology, studying the star's pulsations, could provide insights. Circumstellar environment. The structure and composition of the circumstellar envelope needs better characterization. High-resolution observations in multiple wavelengths could map the dust distribution, identify molecular species, and trace the history of mass loss. Rotation. Is the star rotating significantly? Rotation affects stellar structure and evolution, particularly for massive stars. Spectroscopic observations could potentially measure rotation, though it's difficult for such a large, distant object. Companion objects. Does Stephenson 2-18 have any companion stars? Many massive stars are in binary or multiple systems. A companion could significantly affect the star's evolution and ultimate fate. Careful monitoring for periodic variations or direct imaging could reveal companions if they exist. Magnetic field. Red supergiants are expected to have magnetic fields, but measuring them is extremely difficult. Understanding the magnetic field would help us understand the star's mass loss mechanisms and wind structure. Precise age and evolutionary state. How old is the star exactly, and what stage of its evolution is it in? Is it early in its red supergiant phase or approaching the end? This affects predictions about its future evolution and how long until it explodes. Chapter 20. The Future of Giant Star Research. The study of extreme red supergiants like Stephenson 2-18 is entering an exciting new era. Next-generation telescopes. Several powerful new instruments will revolutionize our understanding. The James Webb Space Telescope, already operational, can observe in infrared wavelengths with unprecedented sensitivity and resolution, piercing dust to reveal stars and their environments. The extremely large telescope, when completed, will have a 39-meter primary mirror, offering incredible resolution and light-gathering power. The Giant Magellan Telescope and 30-meter telescope will add additional, powerful eyes to study these objects. Long baseline infrared interferometry, combining light from multiple telescopes, could potentially resolve the surfaces of nearby red supergiants and maybe even Stephenson 2-18. Computational advances. Better computers and improved numerical techniques are enabling more sophisticated stellar models. Modern simulations can model the 3D structure of stellar atmospheres, track convection in detail, and follow the complex interactions between radiation, matter, and magnetic fields. As these models improve, we'll better understand how red supergiants work and what determines their maximum size. Multi-messenger astronomy. When massive stars explode, they produce not just light, but also neutrinos and gravitational waves. Neutrino detectors like IceCube and future detectors will catch the neutrino burst from nearby supernovae, providing information about core collapse processes. Gravitational wave detectors might detect signals from asymmetric explosions or from the formation of black holes. When a star like Stephenson 2-18 eventually explodes, we'll study it with electromagnetic telescopes, neutrino detectors, and gravitational wave observatories simultaneously, giving an unprecedented complete picture. Long-term monitoring. Systematic surveys are monitoring thousands of stars over years and decades, tracking their variability and evolution. As these datasets grow, we'll better understand the timescales of red supergiant variability, the nature of mass loss, and the events leading up to explosion. Population statistics. We're discovering and characterizing more red supergiants in our galaxy and nearby galaxies. By studying populations of these stars, we can understand how common are extreme red supergiants, what factors determine their maximum size, how does metallicity affect red supergiant properties, what's the relationship between red supergiant properties and supernova types. Conclusion. Chapter 21. The Big Picture. So what have we learned from our deep dive into Stephenson 2-18? We've learned that this is a star at the absolute extreme of what stellar physics allows. A red supergiant so large that if placed where our sun is, it would engulf Saturn. We've learned that it formed in a remarkable star cluster containing dozens of massive stars, all born from the same molecular cloud 15 to 20 million years ago. We've learned that it's powered by nuclear fusion in its core, currently fusing helium into carbon and oxygen, and that it will continue through successive fusion stages until it can fuse no more and its core collapses catastrophically. We've learned that it's losing mass at a tremendous rate, shedding material that will eventually become part of new stars and planets, enriching the galaxy with heavy elements. We've learned that measuring such an object is extraordinarily challenging, requiring sophisticated techniques and careful analysis, and that our measurements still carry significant uncertainties. We've learned that stars like this teach us about stellar evolution, nucleosynthesis, mass loss, dust formation, and the life cycles of massive stars. And we've learned that the universe is capable of creating objects so enormous, so powerful, and so extreme that they challenge our ability to comprehend them. But perhaps most importantly, we've learned something about ourselves. The fact that we, collections of atoms formed in previous generations of stars, can study a star 19,000 light years away, determine its properties, understand its past, and predict its future is itself extraordinary. We're tiny. Earth is a speck compared to Stephenson 218. Our entire solar system would fit comfortably inside this single star. Our lifetimes are fleeting compared to stellar timescales, and yet we understand. We've taken photons that traveled for 19,000 years across space, analyzed them, and from them reconstructed the properties of an object we'll never visit, can never touch, can barely imagine. That's the power of science, the triumph of human curiosity, and the beauty of our quest to understand the cosmos. Stephenson 218 will exist for perhaps another 1,000,000 years before exploding in a supernova that will briefly outshine entire galaxies, long after human civilization has either spread to the stars or returned to dust. This star will still be there, burning quietly in the darkness, a monument to the universe's ability to create wonders. And somewhere, perhaps, other intelligences on distant worlds are looking at their night skies, seeing Stephenson 218 or its eventual supernova, and asking the same questions we ask. How big? How far? How does it work? What does it mean? The largest star in the universe is a reminder that we live in a cosmos of staggering scale and beauty, where the impossible becomes routine and where even the greatest monuments to stellar physics eventually fade away, returning their material to the cycle of cosmic evolution. We've discovered the biggest star we know of, but the universe is vast, and there are hundreds of billions of galaxies, each containing hundreds of billions of stars. Somewhere out there, there might be an even larger star waiting to be discovered. Somewhere, there are wonders we haven't yet imagined, and that's exactly how it should be. Because the universe that can still surprise us, that can still reveal new extremes, new records, new impossibilities made manifest. That's a universe worth exploring. Stephenson 218 is the biggest star we've found so far. The key words are so far. The search continues. The Saut-Tua exploration never ends, and that's the most beautiful thing of all. Chapter 22, The Hidden Companions of Stephenson 2. While Stephenson 2-18 is the undisputed giant of its cluster, it's far from alone. The Stephenson 2 cluster is a treasure trove of extreme stellar objects. And understanding the full picture requires examining its stellar neighborhood. The cluster contains at least 26 confirmed red supergiants, an extraordinary concentration. To put this in perspective, red supergiants are rare objects. In the entire Milky Way galaxy with its 200 to 400 billion stars, there are probably only a few thousand red supergiants at any given time. Finding 26 of them in a single cluster is like finding a neighborhood where every house contains a lottery winner. It's statistically improbable unless something very specific created these conditions. Let's meet some of Stephenson 2.18's siblings, Stephenson 2.3, another massive red supergiant in the cluster, with an estimated radius around 1,200 solar radii. While dwarfed by Stephenson 2.18, it's still enormous by any reasonable standard, larger than the orbit of Mars, if placed where our Sun is. Stephenson 2-9. Estimated at roughly 1,000 solar radii, this star is notable for its extreme variability, changing brightness significantly over periods of months. Stephenson 2-15. Another giant, possibly approaching 1,500 solar radii, though measurements are uncertain. Stephenson 2-17. Close in size to Stephenson 2-18, with some estimates suggesting it might be comparable or even slightly larger, though current data suggests it's probably somewhat smaller. What's fascinating is that all these stars formed from the same giant molecular cloud at roughly the same time. They're stellar siblings, born from the same cosmic nursery 15 to 20 million years ago. But why did this particular cloud produce so many massive stars? The formation. Mystery. Star formation is a complex process influenced by multiple factors. Cloud mass. The original molecular cloud must have been extremely massive, probably tens of thousands to hundreds of thousands of solar masses, to have enough material to form so many large stars. Cloud density. Dense clouds form stars more efficiently. The Stephenson 2 progenitor cloud was likely very dense by molecular cloud standards. Metallicity. The chemical composition affects how clouds cool and fragment. The Stephenson 2 region has roughly solar metallicity, which is conducive to forming massive stars. Turbulence. Low turbulence allows larger clumps to form before fragmenting. The original cloud probably had relatively low internal turbulence. External triggers. Something might have triggered the cloud's collapse, perhaps a nearby supernova shockwave, collision with another cloud, or passage through a spiral arm. The result was a burst of star formation, creating many massive stars in a relatively small region of space. The cluster. Dynamics. Star clusters aren't static. They evolve over time through several processes. Stellar evolution. The most massive stars evolve fastest. In Stephenson 2, the red supergiants we see today were the most massive stars in the cluster. They're now in late evolutionary stages, approaching the end of their lives. Less massive stars in the cluster are still on the main sequence, steadily fusing hydrogen, and won't become red supergiants for tens or hundreds of millions of years more. Mass segregation. In young clusters, dynamical interactions cause massive stars to sink toward the center, while low-mass stars get scattered outward. This process, called mass segregation, concentrates the most massive stars in the cluster core. Stephenson 2 shows evidence of mass segregation, with the red supergiants concentrated in a relatively small region. Cluster dissolution. Over time, gravitational interactions eject stars from the cluster. Low-mass stars are ejected preferentially, gradually dispersing the cluster. Stephenson 2 will likely dissolve over the next few tens of millions of years, scattering its stars across a larger region of the galaxy. Supernova disruption. When the massive stars in the cluster start exploding as supernovae, which will begin happening soon on cosmic timescales. The explosions will inject energy into the cluster, potentially accelerating its dissolution. The supernova chain reaction. Here's where things get really interesting. Over the next few million years, the red supergiants in Stephenson 2 will begin exploding as supernovae. Imagine being able to watch this unfold, from a safe distance, of course. T equals 0. The cluster looks roughly as it does today, with 26 plus red supergiants and numerous other massive stars. T equals 100,000 years. The first red supergiant explodes. The exact timing is unpredictable, but one of the cluster's most massive stars reaches the end of its nuclear fuel and undergoes core collapse. For a few weeks, this single star outshines the entire rest of the cluster. The explosion ejects material at high velocity, creating a rapidly expanding bubble of hot gas. T equals 500,000 years. Several more supernovae have occurred. The cluster is now embedded in a complex overlapping network of supernova remnants. The combined energy from multiple explosions has created a superbubble, a vast cavity of hot, low-density gas hundreds of light years across. T equals 2 million years. Most of the red supergiants have now exploded. The cluster is unrecognizable from its current state. The superbubble has expanded to enormous size, possibly breaking out of the galactic disk and venting hot gas into the galactic halo. The remaining cluster members are dispersing, scattered by the cumulative effects of the supernova explosions. T equals 10 million years. The cluster has dissolved. Its former members are now scattered across hundreds of light years. The Wu superbubble is fading as it expands and cools. All that remains as evidence of the cluster's former existence are the neutron stars and black holes left behind by the supernova, slowly drifting apart. This process, the sequential explosion of massive stars in a cluster, is one of the primary ways that stellar feedback shapes the structure of galaxies. Chapter 23, The Observational History, the story of how we came to understand Stephenson 2 to 18 is itself fascinating, involving decades of observations and evolving technology. 1990, Initial Discovery. Charles Bruce. Stephenson's original survey identified the cluster using photographic plates and infrared data. At the time, he recognized it as a cluster of heavily reddened stars, but didn't have the data to determine individual stellar properties. The cluster was cataloged, but detailed follow-up was limited by the technology of the era. 1990s to 2000s. Infrared surveys. As infrared astronomy advanced, particularly with surveys like 2MASS, 2-micron all-sky survey, astronomers could better study heavily obscured regions like Stephenson 2. Infrared observations revealed the cluster's extent and began identifying individual stars. The presence of many extremely red objects suggested the cluster contained numerous evolved massive stars. 2006 to 2010, spectroscopic studies. Detailed spectroscopic observations began characterizing individual stars in the cluster. By analyzing absorption lines in stellar spectra, astronomers could determine stellar temperatures, compositions, and radial velocities, motion toward or away from us. These studies confirmed that the red stars were indeed red supergiants, cool, evolved massive stars, and that they all shared similar radial velocities, confirming they were physically associated in a cluster rather than being a chance alignment. 2010 to 2015. Size estimates. As astronomers combined spectroscopic data, giving temperatures, with infrared, photometry, giving luminosities after correcting for distance and extinction, they could calculate stellar radii using the Stefan-Boltzmann law. This is when the extreme sizes of several cluster members became apparent. Stephenson 218 emerged as possibly the largest, though measurements carried significant uncertainties. 2015 to 2020. Refinements improved distance estimates using parallax measurements from the Gaia spacecraft, though Stephenson 2 is too distant for direct parallax. And better extinction modeling refined the size estimates. Multiple research groups published studies with varying results, leading to ongoing debate about exactly which stars in the cluster are largest and by how much. 2020 to present. Modern understanding. Current observations using facilities like the Very Large Telescope, infrared space telescopes, and radio interferometry continue refining our understanding. We now have better distance estimates, around 19,000 light-years with approximately 10% uncertainty, improved stellar parameters, temperatures, luminosities, compositions, evidence for circumstellar material around many of the red supergiants, understanding of the cluster's age and formation history, recognition that Stephenson 2-18 is likely one of the largest stars known, possibly the largest, the measurement challenge timeline. It's worth understanding why measuring these stars took so long and why uncertainties remain. Pre-1990. The cluster was essentially invisible in optical wavelengths due to heavy extinction. Without infrared capabilities, astronomers couldn't even detect it properly. 1990 to 2000. Early infrared surveys detected the cluster, but couldn't determine individual stellar properties with precision. 2000 to 2010. Improved infrared spectroscopy allowed temperature measurements, but distance uncertainties and extinction corrections limited size calculations. 2010 to 2020. Better data and modeling improved estimates, but different. Research groups using different methods got different results, highlighting systematic uncertainties. Present. We're converging on consistent values, but significant uncertainties remain, particularly regarding exact sizes of individual stars. Future, next-generation telescopes, particularly the ELT and advanced infrared interferometry, should provide much more precise measurements within the next decade. Chapter 24. The Physics of Red Supergiant Atmospheres. To truly understand Stephenson 2-18, we need to dive into the bizarre physics of red supergiant atmospheres, because they're unlike anything else in the universe. Density profile. In a normal star like the Sun, density decreases relatively smoothly from the core to the surface. There's a well-defined photosphere, the visible surface, where the density drops sharply. In a red supergiant like Stephenson 218, the situation is radically different. The core is extremely dense. roughly 10,000 times, denser than lead. Here, matter is compressed by the immense pressure of the overlying layers. Moving outward, density decreases gradually through the radiation zone and convection zone, but the outer atmosphere is extraordinarily extended and tenuous. At the surface, defined as the photosphere, where the star becomes optically thick, the density is only about 10 to the power of -7 kilograms per cubic meter, roughly 1/millionth the density of Earth's atmosphere at sea level. Further out, in the extended atmosphere above the photosphere, density continues to decrease. At distances of several stellar radii, the density is comparable to the best vacuums we can create in laboratories. Yet this incredibly tenuous material is still technically part of the star. It's gravitationally bound, barely, and contributes to the star's total radius. Temperature structure. The temperature profile is equally strange. In the core, temperatures reach hundreds of millions of Kelvin, hot enough for helium fusion and fusion of heavier elements. Moving outward through the envelope, temperature decreases. The outer convection zone has temperatures ranging from millions of Kelvin in the deep interior to tens of thousands of Kelvin in the upper regions. At the photosphere, the visible surface, temperature is around 3,200 Kelvin. This is why the star appears red. At this temperature, it emits most of its light in the red and infrared portions of the spectrum. But here's where it gets weird. Above the photosphere, in the chromosphere and corona, temperature can actually increase again. Shock waves and magnetic heating can create regions of the outer atmosphere that are hotter than the photosphere below them. This temperature inversion is counterintuitive but well documented in red supergiants. Convection and turbulence. The outer envelope of a red supergiant is a churning, turbulent mess. Convection, hot material rising, cooling, and sinking, operates on enormous scales. Individual convection cells in Stephenson 218 might be larger than the entire Sun. These cells aren't stable. They form, evolve, and dissipate over timescales of months to years. The surface is in constant motion, with material moving at speeds of tens of kilometers per second. This convective turbulence creates several effects. Brightness variations. As hot and cool regions rotate in and out of view, the star's apparent brightness changes. Combined with pulsations, this creates the complex variability observed in red supergiants. Spectral line variations. The turbulent velocity fields create Doppler shifts in spectral lines, broadening them and causing them to vary over time. Mass loss enhancement. Convection brings hot material from deep in the star to the surface, where it can more easily escape. This contributes to the high mass loss rates. Magnetic field generation. The turbulent, electrically conducting plasma generates magnetic fields through dynamo action. These fields are probably weak and tangled compared to younger stars, but they still influence the star's behavior. The molecular layer. In the outermost regions of the atmosphere, where temperatures drop below about 3,000 Kelvin, something remarkable happens. Molecules can exist. In hotter stars, molecules are torn apart by the energetic radiation field. But in red supergiant atmospheres, it's cool enough for molecules to survive. Common molecules include water, H2O, carbon monoxide, CO, silicon oxide, SiO, titanium oxide, TiO, hydroxyl, OH. These molecules absorb light at specific wavelengths, creating dark bands in the star's spectrum. Studying these molecular features tells us about the temperature, density, and composition of the outer atmosphere. The molecular layer is also where dust begins to form. Dust formation. As gas flows outward from the star in the stellar wind, it cools. At a certain distance from the star, typically a few stellar radii out, the temperature drops low enough for dust grains to condense. This is a complex process. First, seed nuclei form. These might be simple molecules like TiO2 or Al2O3 that can exist at relatively high temperatures. Then, these seeds grow as more material condenses onto them, forming larger and larger grains. The composition depends on the star's chemistry. Carbon-rich stars form carbonaceous dust, graphite, amorphous carbon. Oxygen-rich stars form silicate dust, various silicon-oxygen compounds. Stephenson 2-18 appears to be oxygen-rich based on spectroscopic evidence, so it's probably surrounded by silicate dust. This dust has important effects. Radiation pressure. The dust absorbs the star's light and is pushed outward by radiation pressure. This accelerates the stellar wind, helping to drive mass loss. Reprocessing. The dust absorbs ultraviolet and visible light from the star and re-radiates it as infrared. This is why red supergiants are often brightest in the infrared. Opacity? The dust makes the star's environment very opaque, affecting how we observe it and measure its properties. Chapter 25. Comparing giants across the universe. While Stephenson 2-18 is the largest star we know of, it's interesting to compare it to other extreme objects in the universe to gain perspective. Stephenson 2-18 versus the Sun. We've covered this, but let's add more detail. Property: Sun. Stephenson 2-18. Ratio: radius 696,000 kilometers, approximately 1.5 billion kilometers. Nuwarhadkin 2,150 times. Mass: Soyuz 1 solar mass. Soyuz 15 to 20 solar masses. 15 to 20 times. Luminosity: 1 solar luminosity. 500,000 solar luminosities. 500,000 times. Surface temperature: 5,778 Kelvin. 3,200 Kelvin. 0.55 times. Noor. Average density: Trit 1,408 kilograms per cubic meter. 0.00001 kilograms per cubic meter. So 0.000007 times. Surface gravity: 274 meters per second squared. 0.00005 meters per second squared. 0.000002 times. Escape velocity: 618 kilometers per second, approximately 30 kilometers per second, approximately 0.05 times. Some interesting observations. Despite being 2,150 times larger in radius, Stephenson 2-18 is only 15 to 20 times more massive. This is because it's vastly less dense. The surface gravity is incredibly low. You could almost jump off Stephenson 2-18 if you could somehow stand on its surface without being vaporized. The escape velocity is surprisingly low for such a massive object, again because of the enormous size. This low escape velocity facilitates the high mass loss rate. Stephenson 2-18 versus Betelgeuse is often called a red supergiant, and it is one, but it's much smaller than Stephenson 2-18. Property: Betelgeuse. Stephenson 2-18, radius approximately 700 to 900. Solar radii distance approximately 650 light-years, approximately 19,000 light-years. Apparent magnitude, approximately 0.5, varies. Approximately 15. Luminosity, approximately 100,000. L, approximately 500,000. Betelgeuse is famous because it's relatively close and very bright in our sky. If Stephenson 2 to 18 were at Betelgeuse's distance, it would be magnitude -4 or brighter, far brighter than any star, except the Sun. Conversely, if Betelgeuse were at Stephenson 2/18's distance, it would be invisible to the naked eye and require a telescope to observe. Stephenson 2-18 versus planetary nebulae. While Stephenson 2-18 is the largest single star, it's tiny compared to some structures created by stars. The Helix Nebula, a planetary nebula created when a sun-like star shed its outer layers, spans about 2.5 light-years across. Stephenson 2/18's diameter is about 0.0003 light-years, about 2.8 billion kilometers. The Helix Nebula is roughly 8,000 times larger in diameter. This illustrates an important point. While Stephenson 2/18 is enormous for a star, it's tiny compared to the structures stars create when they die. Stephenson 2-18 versus supernova remnants. When Stephenson 2-18 eventually explodes, it will create a supernova remnant that grows far larger than the star itself. The Crab Nebula, the remnant of a supernova that exploded in 1054 CE, is now about 11 light-years across and still expanding. The Stephenson 2/18 supernova remnant will probably reach similar or larger sizes over thousands of years, becoming tens of light-years across. Stephenson 2-18 versus black holes. This comparison is tricky because black holes are measured differently. A black hole with 20 solar masses, possibly what Stephenson 2-18 will leave behind, has an event horizon radius of about 59 kilometers. Stephenson 2-18's radius is about 1.5 billion kilometers, roughly 25 million times larger than the black hole event horizon. However, black holes can have much larger effects. The photon sphere, where light can orbit, is 1.5 times the event horizon radius, approximately 88 kilometers. The innermost stable circular orbit, ISCO, for a non-rotating black hole is 3 times the event horizon radius, approximately 177 kilometers. The sphere of influence, the region where the black hole's gravity dominates, can extend for light years if the black hole is in a low-density environment. And if the black hole accretes material, it can create an accretion disk hundreds or thousands of times larger than the event horizon, plus jets that extend for thousands of light years. So while the black hole itself is tiny compared to Stephenson 2/18, its zone of influence can ultimately be larger. Chapter 26. The Evolutionary Path Forward. Let's map out Stephenson 2/18's future in detail, because its evolution over the next million years will be fascinating. Current state, red supergiant phase. Right now, the star is fusing helium into carbon and oxygen in its core. This is a relatively stable phase that might last anywhere from 100,000 to a few million years, depending on the exact core mass and fusion rate. The core is contracting and heating up as helium fusion proceeds. Surrounding the core are shells where different fusion processes are occurring. A helium-burning shell, a hydrogen-burning shell further out. Inert layers of hydrogen-rich material in the outer envelope. Stage 1. Continued. Evolution. Next 100,000 years. Over the next 100,000 years or so, several things will happen. The star will continue losing mass through its stellar wind. At current rates, roughly 1 Earth mass every few thousand years, it might lose several tens of Earth masses over this period. The core will gradually exhaust its helium fuel. As helium becomes depleted, the fusion rate will increase in an attempt to maintain pressure support, making the star more luminous. The star might undergo variations in size and temperature. Some models predict blue loops, where red supergiants temporarily contract and become hotter before expanding again. The mass loss rate might increase as the star becomes more luminous and approaches closer to the Eddington limit. Stage 2. Advanced burning stages. Next 100,000 to 1 million years. Once helium is exhausted in the core, carbon fusion begins. This marks the beginning of the end. Carbon burning, carbon fuses into neon, sodium, and magnesium. This phase might last 10,000 to 100,000 years, depending on core mass and temperature. During carbon burning, the star might experience increased instability. The outer layers could pulsate more violently, and mass loss might increase dramatically. Neon burning. Neon photodisintegrates and rearranges into oxygen and magnesium. This phase lasts only a few years to decades. Oxygen burning. Oxygen fuses into silicon, sulfur, and other elements. This phase lasts months to years. Silicon burning. Silicon fuses into iron peak elements. This is the final fusion stage, lasting about 1 day. Each successive stage happens faster because 1. Higher temperatures are required, which means the core is more compact and denser too. The energy output per fusion reaction decreases for heavier elements 3. Energy losses through neutrino emission increase dramatically at high temperatures. Stage 3. Pre-supernova, final years to days. In the final years before explosion, the star might undergo dramatic changes. Increased mass loss. The mass loss rate could spike to extraordinary levels. Some massive stars lose several solar masses in the final few years before exploding. Extreme variability. The star might vary wildly in brightness as internal instabilities grow. Possible LBV phase. Some massive stars transition through a luminous blue variable phase, characterized by dramatic eruptions. Whether Stephenson 218 will do this is uncertain. Shell ejections. The star might eject shells or clumps of material that will later interact with the supernova ejecta, creating complex structures. In the final days before core collapse, silicon is fusing into iron in the core. The star knows on some level that disaster is imminent. Neutrino losses are extreme. The core is contracting. Pressure is building. But outwardly, the star probably looks much as it did before. Someone observing from afar would see a red supergiant, perhaps varying in brightness, perhaps surrounded by evidence of increased mass loss, but showing no obvious sign that its end is mere days away. Stage 4, core collapse, final day. Then, in less than a second, everything changes. The iron core reaches 1.4 solar masses. Electron degeneracy pressure, which had been supporting the core, is overwhelmed. In 0.25 seconds, the core implodes from roughly Earth size to 20 kilometers across. The collapse releases about 10 to the power of 46 joules of energy, more energy than the sun will produce in its entire 10 billion year lifetime, mostly in the form of neutrinos. The shock wave forms and begins propagating outward through the 15 to 20 solar masses of overlying material. Stage 5, supernova, hours to weeks. The shock reaches the surface about 10 hours after core collapse. The star begins to brighten dramatically. Over the next few days, the supernova reaches peak brightness, about 10 billion times the sun's luminosity. For a few weeks, this single, exploding star outshines entire galaxies. The spectrum evolves as different layers of the ejected material become visible. Initially, we see the outer hydrogen envelope. Later, as it becomes transparent, we see deeper layers enriched with helium, oxygen, and heavier elements. The ejecta expands at 10,000 to 30,000 kilometers per second, sweeping up surrounding material and creating a shock wave that will propagate through the interstellar medium for tens of thousands of years. Stage 6, remnant, millennia onward. After the initial explosion fades, what remains? At the center, a neutron star or black hole, the collapsed core that triggered the explosion. Surrounding it, an expanding cloud of ejected material, the supernova remnant, glowing in X-rays, visible light, and radio waves as it interacts with the surrounding medium. This remnant will expand for tens of thousands of years, gradually fading and merging with the interstellar medium. The heavy elements created in the star and the explosion, carbon, oxygen, iron, gold, and many others, will mix into the galactic gas, eventually becoming part of new stars and planets. Somewhere, billions of years in the future, an atom forged in Stephenson 218 might become part of a living organism on some distant world, contemplating its origins just as we contemplate ours. Chapter 28. Standing on the Shoulders of Supergiants. There's a beautiful irony in studying Stephenson 218 that we need to address. We are, quite literally, made of stars like it. Every atom in your body heavier than hydrogen was forged inside a star. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was created through nuclear fusion in stellar cores, then scattered across the galaxy when those stars exploded. And not just any stars. Small stars like red dwarfs never get hot enough to create elements heavier than helium. Even sun-like stars only produce carbon and oxygen in their final stages. To create the full diversity of elements that make up planets and life, you need massive stars, stars that live fast, burn bright, and die explosively. Stars like Stephenson 218. The oxygen you're breathing right now was fused from helium inside a red supergiant billions of years ago. The nitrogen in the proteins that make up your muscles was created in similar stellar forges. The phosphorus in your cell membranes, the sulfur in your amino acids, the trace elements that enable your biochemistry, all stellar products. When Stephenson 218 eventually explodes, it will enrich the interstellar medium with fresh batches of these elements. Billions of years from now, those atoms might become part of planets orbiting stars that haven't even formed yet. They might become part of organisms we can't imagine, living lives we can't comprehend, in a galaxy transformed by time. This is the ultimate legacy of red supergiants. Not the spectacular light show of their explosions, not the exotic, remnants they leave behind, but the quiet, enduring contribution to the chemical complexity of the universe. We exist because stars like Stephenson 218 existed before us. Our very atoms are recycled stellar material, forged in nuclear furnaces and distributed by cosmic explosions. The perspective shift understanding. This creates a profound shift in perspective. When you look at Stephenson 218's estimated lifespan, perhaps 20 million years total from birth to supernova, it seems incredibly short by human standards for something so massive and powerful. But consider, in those 20 million years, this single star will have contributed to the cosmic cycle of matter and energy in ways that will echo for billions of years afterward. The elements it creates will persist long after the star itself is gone. They'll be incorporated into new stars, planets, asteroids, comets. They'll drift through interstellar space for eons. They'll be part of the galaxy's evolution for timescales that dwarf the star's lifetime by factors of thousands. In a real sense, stars like Stephenson 2-18 are more important dead than alive. Their true contribution comes not during their luminous lifetimes, but in the aftermath of their destruction, when they seed the cosmos with the building blocks of complexity. This is why astronomers care so much about understanding stellar evolution, mass loss, and supernova nucleosynthesis. It's not just academic curiosity, it's understanding the processes that made our existence possible. Chapter 29: The Unanswered Philosophical Questions. Studying Stephenson 2-18 raises questions that go beyond physics and astronomy into philosophy and meaning. The anthropic question: why does the universe allow objects like Stephenson 2-18 to exist? Why are the laws of physics calibrated such that stars can become this large but not larger? Why is there an upper limit at all? These aren't scientific questions with empirical answers. They're deeper questions about why reality has the structure it does. Some physicists appeal to the anthropic principle. The universe must be compatible with the existence of observers, or there would be no one to observe it. If stellar physics were different, perhaps carbon-based life couldn't exist, and we wouldn't be here to ask the question. Others suggest we live in a multiverse where different regions have different physical laws, and we happen to inhabit one where red supergiants can exist. Still others simply accept that these are the laws we observe, and asking why is meaningless. It's just how things are. Stephenson 2-18 doesn't answer these questions, but it does make them more concrete. When you contemplate an object operating at the absolute limits of physical possibility, you can't help but wonder about those limits and why they exist. The scale. Question. Humans evolved to understand the scale of things that mattered for survival, distances you could walk, sizes of animals and plants, timescales of days and seasons. We have no evolutionary preparation for understanding cosmic scales. 1 billion kilometers is meaningless to our intuitions. 1 million years is incomprehensible. A stellar luminosity 500,000 times greater than the sun is just abstract numbers. Yet we can understand these things mathematically and scientifically, even if we can't truly visualize or feel them. What does it mean that we can understand things we can't really comprehend? That we can measure and model objects whose scales are utterly foreign to our experience? It suggests that human cognition is flexible and powerful in ways that go far beyond what evolution designed it for. We can bootstrap our understanding from the familiar to the cosmic, using mathematics and abstraction as tools. Stephenson 2.18 is a testament to this capacity. It exists at scales completely divorced from human experience, yet we've measured it, understood it, and predicted its future with remarkable accuracy. The loneliness. Question. Stephenson 2-18 exists in a region of space that may never be visited by any conscious being. At 19,000 light-years away, traveling there would take millions of years, even at substantial fractions of light speed. By the time any hypothetical probe arrived, the star might have already exploded. It exists. It's magnificent. It's operating at the extremes of stellar physics, creating elements and energy on scales that beggar imagination. And for all we know, no being will ever stand in proximity to it, witness it directly, or appreciate its existence except through the attenuated photons that reach distant telescopes. Does that matter? Does the universe care whether its wonders are witnessed? These are not scientific questions, but they're prompted by the science. When you study distant cosmic objects, you can't escape confronting the vastness and indifference of the universe. Stephenson 2.18 doesn't exist for us. It doesn't care that we've discovered it or that we find it interesting. It simply exists, following the laws of physics, burning its fuel, approaching its end, completely independent of human awareness. And yet, the fact that we're aware of it, that we can study it and appreciate it, feels meaningful somehow. The universe has produced in us something that can contemplate the universe itself. Chapter 30, The Future of Discovery. As we close this exploration of Stephenson 2.18, it's worth considering what the future might hold for the study of extreme stars. Next generation observations. Within the next decade, several new capabilities will revolutionize our understanding. The Extremely Large Telescope will achieve first light around 2028, offering unprecedented resolution and sensitivity. It will be able to study individual stars in distant clusters with far more detail than currently possible. Advanced infrared interferometry, combining light from multiple telescopes, might actually resolve the surfaces of red supergiants, allowing us to see their convection patterns and atmospheric structure directly. Time domain astronomy, systematically monitoring the sky for changes, will catch more red supergiants in unusual states, during eruptions, or even during the early stages of core collapse. Improved computational models will better predict stellar evolution, mass loss, and supernova outcomes, allowing more accurate interpretation of observations. Potential discoveries. What might we find? Larger stars. While Stephenson 2-18 is probably close to the theoretical maximum size, we might discover stars that push the limits even further, helping us understand exactly where the boundary lies. Pre-supernova behavior. With luck and good timing, we might catch a red supergiant in its final years, or days before explosion, allowing unprecedented study of pre-supernova evolution. Exotic variations. There might be red supergiants with unusual properties we haven't seen yet. Rapidly rotating ones, those in unusual binary systems, or those with peculiar chemical compositions. Distant examples. As our telescopes improve, we'll be able to study red supergiants in more distant galaxies, seeing how stellar evolution differs in environments with different metallicities and star formation histories. The supernova watch. Eventually, and this could be tomorrow or in 1,000,000 years, Stephenson 218 will explode. When it does, assuming humanity still exists and still has functioning telescopes, it will be an unprecedented opportunity. We'll have studied the progenitor star in detail. We'll have measurements of its mass, size, composition, and mass loss history. Then we'll observe the explosion itself, seeing exactly what kind of supernova this particular type of star produces. This one-to-one correlation between pre-supernova state and explosion characteristics is incredibly valuable for understanding supernova physics. Every red supergiant that explodes teaches us something. Betelgeuse could explode at any time, though any time in astronomical terms means sometime in the next 100,000 years. When it does, it will be visible in daylight from Earth and studied in unprecedented detail. Stephenson 218 is too distant for such spectacular visibility, but it will be intensely studied nonetheless. The broader context. The study of extreme stars like Stephenson 2-18 fits into the broader quest to understand the universe. How do stars form and evolve? How do they enrich the cosmos with heavy elements? What determines their ultimate fates? How do stellar populations shape galaxies? These aren't abstract academic questions. They're fundamental to understanding our cosmic origins and our place in the universe. Every new observation, every refined measurement, every improved model brings us closer to complete understanding. We'll probably never know everything about Stephenson 2-18. Some uncertainties may persist indefinitely, but we know vastly more than we did 30 years ago, and we'll know vastly more 30 years from now. That trajectory of increasing understanding is what makes science beautiful. We're always approaching truth, always refining our models, always discovering new layers of complexity. The final word, Stephenson 218, exists as it always has, burning in the darkness, approaching its spectacular end, utterly indifferent to our existence. But we're not indifferent to it. We've measured it, studied it, understood it, and appreciated it. We've connected it to our own origins, recognized it as part of the cosmic cycle that made our existence possible. We've pushed our technology and our understanding to their limits to comprehend something completely beyond human scale. And in doing so, we've demonstrated something profound about what it means to be human. We are curious, we are capable, and we are part of this magnificent universe, not separate from it. The largest star in the known universe is out there right now, fusing helium, losing mass, approaching its supernova, completely unaware that on a small planet 19,000 light-years away, beings made from the ashes of stars, like it, are looking back, understanding, and marveling. That connection between the vast and the small, between the cosmic and the human, between the object and the observer, is perhaps the most beautiful thing about the universe. We've discovered the biggest star, but more importantly, we've discovered that we can discover it, understand it, and appreciate it. And that capacity for discovery, understanding, and appreciation might be the most remarkable thing in the universe. Final reflection. Chapter 27. What it all means. We've journeyed deep into the heart of the largest star in the known universe. We've explored its properties, its environment, its past, and its future. We've compared it to other cosmic, objects and understood its place in the broader context of stellar evolution and galactic ecology. But what does it all mean? On one level, Stephenson 218 is just a star. It's a massive ball of gas undergoing nuclear fusion, governed by the same physical laws that govern everything else in the universe. There's nothing supernatural or mystical about it. It's just physics operating at an extreme scale. And yet, there's something profound about contemplating an object like this. This star contains more than a quintillion cubic kilometers of matter. It's so large that light takes 9 hours to cross it. It outputs as much energy every second as the sun produces in 6 days. When it explodes, it will briefly rival the combined light of 200 billion stars. And we, creatures who live at most a century, on a planet that would fit across this star's diameter 110,000 times, we understand it. We've never visited it, can never visit it, but we've measured it, modeled it, and predicted its future with reasonable accuracy. That capacity for understanding is perhaps the most remarkable thing of all. The universe contains objects of staggering scale and power, operating on timescales that dwarf human lifetimes, at distances that make our entire planet seem insignificant. But we're not insignificant. We're the parts of the universe that have become conscious, that can look outward and understand what we see, that can trace the connections between a star exploding billions of years ago and the atoms in our bodies today. Stephenson 2-18 will exist for perhaps another million years. Humanity, in our current form, has existed for maybe 300,000 years. Our technological civilization is barely 10,000 years old. In the grand cosmic timeline, we're fleeting, ephemeral, here and gone in the blink of an eye. But we're here now. And right now, we're looking at Stephenson 218, understanding it, appreciating it, marveling at it. That's not nothing. That's everything. The largest star in the universe is a reminder that we live in a cosmos of wonders, that reality is stranger and more beautiful than we could have invented, and that the human capacity for understanding has no apparent limits. We've discovered the biggest star. We'll probably discover bigger ones. We'll continue exploring, questioning, measuring, and understanding. And that journey of discovery, that endless quest to comprehend the universe we find ourselves in, that might be the most meaningful thing we do. Stephenson 2-18 burns on in the darkness, 19,000 light years away, utterly indifferent to our existence. But we're not indifferent to it, and that makes all the difference.